Assalamualaikum. My name is Anam Javed and my registration number is 16TE82. Welcome to the lecture of Digital Signal Processing. In today's lecture, we will discuss IIR filters. These filters involve input and output versions. First, let's look at the differences of IIR filters in comparison with the FIR filters. In IIR filters, number of filter coefficient decreased. It gives better results. IIR filters can be stable or unstable, but FIR filters can only be stable. The next main topic is bilinear transformation. It involves the following steps. It first involves the transformation of digital specifications into analog specifications by using frequency wrapping. Then these analog frequency specifications are transformed by using low-pass prototype filters into analog filter transfer function, and then bilinear transformation is applied to get digital filter transfer function and frequency response. These prototypes are used. We have the following filters: low pass, high pass, band pass and band stop. We will use the corresponding formulas. When we have a low pass filter, we will use this prototype, that is S over omega C, where omega C is the cutoff frequency. For high pass filter, it will reverse, as low pass and high pass are inverse of each other. The prototype for high pass will be omega C by S, and for band pass the prototype will be S square plus omega naught square divided by SW, where omega naught will come from under root of omega L into omega H. Omega L represents low frequency, omega H represents the high frequency, and capital W comes from the difference of high frequency and low frequency. For band stop filter, the above formula or the above prototype is just reversed, that is S of W divided by S square plus omega naught square, and omega naught and W will remain the same. Let's take an example to explain the previous discussion. Here a low pass prototype filter is given, and we will have to determine the analog filter specifications by converting it into a high pass filter and a band pass filter. Firstly, we will apply the low pass prototype transformation just by substituting S equals to 40 by S. 40 is the cutoff frequency, that is omega C. We will just put this in the formula and get our analog high pass filter. And the second part is to get a band pass filter. We will apply band pass filter specification, that is the prototype formula, by putting the value of omega and S square. We will get this 20S divided by S square plus 20S plus 100. The next main thing is bilinear transformation and frequency wrapping. It involves the mapping of S plane into Z plane. Area under the curve can be determined by using the following integration. Y of t equals to integral of x of t d of t, and integral ranges from 0 to t. This above equation is graphically represented here. The x-axis represents the time division, and y of n is the current version, and y minus n indicates the previous version, and t is the time interval. Let's take another example to explain the bilinear transformation process. Here an analog filter transfer function is given. Now we have to convert it into a digital filter transfer function and difference equation with the sampling period of 0.01 seconds. First we apply the bilinear transformation by just putting S equals to 2 by t z minus 1 z plus 1 in the above equation, and simultaneously substituting the value of t that is given in the question 0.01. We will finally get our transfer function equals to 0.0476 plus 0.0476 z raised to power minus 1 divided by 1 minus 0.9048 z raised to the power minus 1. Now we have to find the difference equation. We will find the difference equation by just taking our denominator to the left side. We will reduce it into a difference equation. This is the pole zero diagram. x-axis represents the real numbers and the y-axis represents the imaginary, that is omega j components. This is a unit circle and omega d represents the angular frequency. Now let's summarize the bilinear transformation design procedure by using the following steps. First, we are given the digital frequency specification. We will pre-wrap the digital frequency specification to the analog frequency specification by using the following formulas. For high pass filter and low pass filter, we will use this formula to convert the digital frequencies into analog frequencies. Omega A represents the analog frequency and omega D represents the digital frequencies. For high pass and low pass filter, we will use this formula: omega A equals to 2 by T tan of omega dt divided by 2. And for band pass filter and band stop filter, we will use these formulas: omega AL equals to 2 by T tan of omega LT divided by 2, and the other formula is omega AH equals to 2 by T tan of omega HT divided by 2. Omega AL represents the low analog frequency and omega AH represents the high analog frequency. Similarly, omega naught and W will remain the same. We will discuss in the previous topic. Now the second point is perform the prototype transformation using the low pass prototypes. As we discussed this prototype earlier, for the low pass filter we will just replace S with S over omega, and for high pass we will just replace S with omega A by S, and for band pass filter we will replace S by S square plus omega naught square divided by SW, and for band stop filter we will just replace S equals to SW divided by S square plus omega naught square. Lastly, we will find the bilinear transformation to obtain the digital filter by replacing S with 2 by T z minus 1 to z plus 1. This is all for today's lecture. Thank you for watching.